more challenging radical equations. So in this video, we're about to see some radical equations that can get more difficult. But the most simple and straightforward advice that I can give you is to isolate the most complex radical and then square both sides of the equation to make that complex radical, or to make that radical go away. And then don't forget, always, always, always check your solution or solutions, because there might be more than one solution to some of these equations. So here in our first example, it doesn't look too bad, right? And we're going to start just by isolating the radical like we were doing before. So subtract 1 from each side, and we get that the square root of p minus 1 is equal to p minus 1. But what's making this a little bit more difficult is that now that we try to go and square each side, it's not just a number on the right-hand side. So we can still get rid of the radical and be left with p minus 1. But on the right-hand side, we actually have a square of a binomial. So I'm going to write that as p minus 1 times p minus 1, and then FOIL this right-hand side of the equation. So p times p is p squared, p times minus 1 is negative p, minus 1 times p is negative p, and then negative 1 times negative 1 is positive 1. So I had to end up foiling the right-hand side of the equation. And what I'm left with is actually a quadratic equation. This would be p minus 1 is equal to p squared minus 2p plus 1. And in order to solve a radical equation, or sorry, I should say, in order to solve a quadratic equation, the way to do that I know how to do so far in this course is to make one side of the equation equal to 0. So now I have 0 equals p squared and minus 2p minus p is minus 3p, and plus 1 is plus 2. And the way I know how to solve these quadratic equations is by factoring. So now I want to factor the right-hand side. So two numbers that multiply to positive 2, add to negative 3, that would be p minus 1 and p minus 2. And if those two brackets multiplied together equals 0, then either p equals 1 or p equals 2. Those are my two potential solutions to this problem. So now we're seeing that we need to be able to factor and solve quadratic equations in order to solve a radical equation. So we're pulling material from stuff that we've done previously into this unit now. But we're not done this problem until we check our solution. Always, always, always check. So first I'm going to check p equals 1, because we have two potential solutions here. So first I'm going to check p equals 1, and does the square root of 1 minus 1 plus 1 equal 1? Well, the square root of 0 plus 1 does in fact equal 1, so p equals 1 is a valid solution. But I also have to check p equals 2. And again, putting it back into the original equation, so we're checking with our original equation. It's the square root of, now it will be 2 minus 1 plus 1. Does that equal 2? So 2 minus 1 is 1, square root of 1 plus 1 equals 2, square root of 1 is 1 plus 1. That does indeed equal 2. So both are valid solutions, and so I can put my box around my final answer. I've confirmed with my check on the side, and so that's the way you want to show your solution and your check. This question is going to require a similar solution, which is first we're just going to try to isolate the radical. So to do that, we're going to have to add r and subtract 2 to each side. So I have the root of r plus 4 is equal to r minus 2. And then I square each side. So square and square. And to square a binomial, I always want to FOIL. So I have r plus 4 is equal to, and then I have to square this binomial. So that's r squared minus 2r minus 2r plus 4. So I have r plus 4 equals r squared minus 4r plus 4. Subtract r, subtract 4, subtract r, subtract 4. Leave me with 0 equals r squared minus 5r, and ooh, the 4's cancels. That's actually quite nice. This is a pretty simple equation to solve because I don't have to factor using any of our simpler messy trinomial strategies. I can just factor r off of each term, leaving me with r minus 5. And so either r equals 0 or r equals positive 5 would be my two solutions, or my two potential solutions. But of course, I have to go back now and check. And I'll start by checking r equals 0. So in that original equation, it would be 0 plus 4 is 4, minus 0 plus 2 equals 0. And so does the square root of 4, which is 2, plus 2 equals 0? No, it most certainly does not. So I have to reject this solution. So again, just show your work. Show that you're checking, and then show that you're rejecting a solution. And that's enough to show your understanding there. That doesn't mean we can reject r equals 5 yet. We have to check it as well. So does the square root of 5 plus 4 minus 5 plus 2 equals 0? And let's go through and simplify. So that would be the square root of 9 minus 5 plus 2 equals 0. So this would be the square root of 9 is 3 minus 5 plus 2 equals 0. And in fact, 3 minus 5 plus 2 does equal 0. 0 equals 0. So r equals 5 is a perfectly valid solution. So interestingly, we had two solutions. One of them we had to reject because it didn't make sense when we put it in the original equation, but the second one we get to keep. So this only has one valid solution. So in this next example, we're going to start to see these examples grow a little bit in terms of how much it takes to solve them. And that's because now we actually have two radicals in this equation. And if you recall back to the advice I gave earlier, I'm going to repeat it here, but the strategy we really suggest, and there's multiple ways to solve this, but the easiest way is to isolate the most complex radical. And what I mean by most complex is the radical with the most going on underneath the radical. So right now, I could just square both sides and eliminate the radical on the left, but I would be left with something really messy if I squared the right-hand side. So what I suggest you do is add 1 to each side, and we'll get square root of m plus 1 is equal to the square root of m plus 9. And now the more complicated or complex radical is isolated on the right-hand side, and now we should go ahead and square both sides. And that's just about making this as simple as possible, as quick as possible. So on the right-hand side now I'm left with m plus 9, and that's great. On the left-hand side I've got some multiplication to do because I have to FOIL this two-term item squared. So now I've got to go ahead and FOIL this. First would be root m times root m is just m. And then I have root m times 1, so that's plus root m plus root m plus 1. So I've gone ahead and FOILed that left-hand side. Now I can simplify, so that would be 2 root m plus 1 equals m plus 9. So you can see that even though I squared each side, I'm still left with a radical on the left-hand side. And that's why these examples can sometimes start to get a little long because even though I've got rid of the most complex radical, I still am solving a radical equation, and the way I do that is by isolating the radical. So subtract m, subtract 1, and subtract m, subtract 1. Sorry, I lost my voice a little there. So m's actually cancel, which is really nice. And so I'm left with 2 root m equals 9 minus 1 is 8. And I divide by 2, left with root m equals 4. And now I can square each side to get rid of that radical, and I'm left with m equals 16. So I got a little lucky because those m's canceled in this example. So it wasn't too complex, but you go from having to solve a radical equation to having to still solve a radical equation, but a slightly less complex one. So there's basically, like, in these examples, in these more complex ones, it's almost like you have to solve 2 radical equations, because that first time you square, like up here in this step, the first time we squared each side of the equation, it didn't get rid of our radical. So you just have to be patient and work your way through these questions. Now let's go ahead and check our solution, because we're not done until we do that. So let's check m equals 16 in our equation. So that would be the square root of 16 is equal to 16 plus 9, square root of 16 plus 9 minus 1. Well, the square root of 16 is 4. And on the right-hand side, I have the square root of 16 plus 9, which is 25 minus 1. So that would be 4 equals, well, the square root of 25 is 5 minus 1, and 5 minus 1 does indeed equal 4. So our solution is valid. Let's go down and highlight that. And in this last example, I just want to show you the most complicated or most difficult that these examples can get. So again, that general advice is just to start by isolating the most complex radical, and in this case that's already done. But you notice that we have 2 radicals with terms underneath them, and there's no getting around these problems. They're going to take a lot of work. And so I have 2 radicals. The one that's the most complex is already isolated. So let's just go ahead and square both sides of this equation. And it's not going to be pretty on that left-hand side. So I'm going to give myself lots of room. In fact, I think I'm just going to rewrite this. So I have the square root of q minus 2 plus 3. To square that, I have to multiply it by the square root of q minus 2 plus 3. And that's equal to, well, here we've had that simplification, so that's equal to 4q plus 1. And now I have to FOIL. So I've got first square root of q minus 2 times square root of q minus 2 is just q minus 2. Those square roots cancel. But then my outsides, I have 3 times, so that's plus 3 times the square root of q minus 2. Insides, I have again plus 3 square root of q minus 2. And last, plus 9 is equal to 4q plus 1. And simplifying this left-hand side, 3 plus 3 is 6, square root of q minus 2. Plus 9 equals 4q plus 1. And now we're just going to isolate that last radical. So subtract q from here, subtract q, add 2, subtract 9, subtract 9. Let's start there, and I'd be left with 6 root q minus 2 is equal to, well, 3q, and then 1 plus 2 is 3, minus 9 is negative 6. And now divide by 6. and I'm left with the square root of q minus 2 is equal to 3q minus 6 over 6, which I can simplify. This is an expression I can simplify. I'm going to divide each top and bottom by 3. So that's square root of q minus 2 is equal to q minus 2 over 2. And now I'm ready to square each side of the equation again, which, you know, it's just not kind. So that gets rid of this radical, leaving me with q minus 2. And now I have q minus 2 squared. So I'm going to write that as q minus 2 times q minus 2 over 2 squared, which is 4. And there's, again, just no getting around that this is a long problem. So to solve this, I'm going to multiply each side by 4 so that I can, that would be negative 8, so that I can multiply these two binomials in piece. And I'm going to continue that up here. So I have 4q minus 8 is equal to, and I'm going to FOIL this guy out quickly here, q minus 2q minus 2q plus 4. So I have 4q minus 8 equals q squared minus 4q plus 4. This is a quadratic, so I collect my like terms. Minus 4q plus 8. And I'm left with 0 on the left-hand side, and I have q squared minus 8q plus 12. And I can factor this, so I have 0 equals q minus 6 times q minus 2. So I have two potential solutions, either q equals 6 or q equals 2. So there we go. This is a long problem, requires a lot of precise mathematics. And I wanted to show you this example because you are going to be expected to solve examples that get as difficult as this, because you have all the skills to do it. It just requires some patience and some precision and a little bit of planning as well. So looking ahead and thinking about what kind of math is going to be coming up. So it goes from solving this radical equation into solving a simpler radical equation. So, you know, I'll sort of highlight that. It starts as solving a radical equation up here, a complex one, to solving a simpler radical equation about here. And it evolves into solving a quadratic equation here. And once we have those solutions, we're still not done because we still have to check them. Now, I think I've taken up enough of your time with this example, so I'm going to let you try those checks on your own to see whether or not the two solutions are valid.